Hello everyone, thanks for joining. Our team would like to present our project called ShmotBot, which is a deep learning based service for finding clothes by picture. Let me briefly describe the service's architecture. Firstly, through a Telegram bot we have written, a user inputs the image, which is then sent to the object detection model. That model outputs the cropped clothes items and their labels and sends them to the embedding model, which creates a vector embedding of the crops. The embedding is then passed to the recommendation system, which looks for the closest embeddings of the images from our database, and sends back the links to the clothes items with a geographical position of the store to find them back to the bot. In this presentation, we'll focus on describing the machine learning part of the architecture, and you can read other aspects in the report. For object detection task, we decided to compare performance of faster RCNN model and the new YOLO v5 one. We chose Deep Fashion 2 dataset for training and evaluation of models. It consists of 491,000 images classified into 13 popular clothing categories. For each image, we have bounding boxes and labels. Faster RCNN consists of two modules, Region Proposing DL Network and Fast RCNN Detector, which uses the proposed regions. The network architecture of YOLO version 5 consists of three parts: CSP darknet as the backbone, PANet as the neck, and the YOLO layer as the head. The data is first inputted to CSP darknet for feature extraction, and then fed to PANet for feature fusion. Finally, YOLO layer outputs detection results: class, score, location, and size. We used faster RCNN as a baseline model. ResNet 50 and MobileNet version 3 small were used as backbones for performance comparison with YOLO version 5. The backbones were pre-trained on COCO dataset. We've trained the small YOLO version 5 net with pre-trained weights on COCO dataset from scratch. Network was trained using SGD optimizer with focal loss. The model trained from scratch has shown better results compared to pre-trained one. Training time was 24 hours and inference time was 4.3 milliseconds. As you can see, we've got good results that are superior to the older networks. Proposed models were compared on 5 metrics: mean average precision score on intersection over union between 0.5 and 0.95 and equal to 0.5, as well as model size, inference time, and number of trainable parameters. As expected, YOLO version 5 model outperformed the baseline models on each metric. Here we can see the bounding box regions for test images taken from real world. The images within bounding boxes were cropped and sent further to the second NN model.
The embedding model is meant to create the vector embeddings of the images, which can later be used by the recommendation system. As we can see from the architecture, the model is applied twice, both to embed the images from the database and to embed the detected parts from the object detection model. And we have considered 3 different approaches for choosing the embedding model. The regular convolutional approach is based on training with a single flow of information, as we pass a single batch to the networks, and apparently the architecture can only be trained with one data flow. The Siamese approach is based on the idea to add the second flow of information to the network. This could potentially increase the quality of the embeddings, and the network is trained on 2 datasets and is encouraged to learn the correspondences between their images. And finally, the non-deep learning approach was chosen to test the overall adequacy of using the deep learning methods for the task. On this slide, you can see which models we have chosen for each category, and we'll skip the description of the regular mobile net and just mention that MD is just a dimensionality reduction method. The Barlow twins is a self-supervised method which is built upon the backbone and allows to learn the representations which are invariant to the input distortions. This is achieved by passing the distorted views of the original image through the network and explicitly adding the invariance term to the loss function. Next. The Siamese networks are generally used for the person re-identification tasks. During training time, two images are passed to the network: the original enter one and another image, which has either positive or the negative label. The identifier of whether another image is positive or negative depends on whether such identity is depicted on the next picture. The network outputs the embeddings of the past images, and it is trained with the optimization of the contrastive loss. During evaluation time, a test image is passed through the network, through this line, and the embeddings are outputted. For the baseline, we have chosen the Msp Cnn architecture, and the peculiar thing about it is that it features the computation of 3 losses, which allow to impose the additional constraints for the training and enhance the resulting embeddings. For the SciSIAM, which consists of a pre-trained encoder and the predictor, it does not use the negative pairs during training. It processes 2 augmented views of the same image and directly computes the contrastive loss between them. This architecture shows the competitive results and is apparently much easier to train. We have used 2 datasets to train the embedding: the deep fashion 2, which we have discussed previously, and the parsed database from Lamoda, which features the same close categories as the deep fashion 2 dataset. We planned to use the accuracy metric for the modal comparison. We calculated the accuracy by taking the embedding of the random image from the batch and calculating the cosine distance from all the other images in the batch. And then we investigated the identity to the closest image. If it was positive image, it belongs to the same category. We added 1 point to the counter, and otherwise we did nothing. And the procedure was done for 4 random images in a batch, and the total accuracy was an average of the counter over all considered images. This we call the adjusted accuracy. Following the Msp Cnn paper, we planned to train the models for 250 epochs, but we found that training takes extensive amount of time, and 1 epoch took more than 2 hours for some SIAM and 54 minutes for Msp Cnn, and this is inadequate given our time and computation restrictions. Therefore, we could not train the model in time. We decided to choose the best model following the 2 criteria: the availability of the weights of the pre-trained model and the inference time for 100 random images. And the results of this comparison show that the models have comparable relative time. So we have chosen the Barlow twins, which is more reliable since it was trained for 1,000 of epochs.
So let's now talk about something which goes around our neural network part. And to start with, our main source of input, the Telegram bot, which is an Telegram-based Telegram bot. It is a multi-thread framework which allows several users to work with us at the same time without any kind of queuing or delaying. So we also built a finite state machine to interact with the user a bit, like to talk to him, to navigate him through our system, like give simple commands, send pictures, wait a bit, and this stuff. It's still like a bit raw, but it's enough to navigate like the newbie in our system. To talk about built-in geolocation services, we'll ask our user to send us location, then we search using the Manhattan distance, the closest store out of a small database to advise to our user, like give him a small recommendation where can he gain the clothing items we recommended to him. And also we provide like working hours and stuff, something to use. Okay, so let's assume we consumed the image from the user, then we detect clothing on it, then we, for each box and label of the piece of cloth, we build an embedding, and after we get like several embeddings, we need to somehow build the recommendation to put out to output to the user. Of course, for this kind of stuff, we need some kind of a database, which we attained using simple tools like Selenium, Beautiful Soup 4 and stuff. we used we made a little advantage of how Lamoda's HTML is built. Not only we collected all like 67,000 of images, which were automatically sorted into categories of the data set used to train the first network in our pipeline. We also found out that all the images are stacked with their unique names, and these unique names contain some more information which can be used in our advance. For example, the gender connection. So if the clothing is supposed to be worn by a man, there is like a special mark in the unique URL of the image. So we also use this information. We used, for example, this information we used as an output filter. We found the recommendations, and then we filtered them by the gender of our user, which we also asked from him in the beginning. So the question is how we found the closest images by our recommendation system. This is kind of a heuristic approach. We used cosine similarity metrics. If the user came to us for the first time, we just searched for top 5, top 10 nearest neighbors, depending on how broad our output should be. It's a hyperparameter, but it can be tuned. And if the user came to us for the first time, it's just the output for him. We construct the links to the products via these unique names of the products, and we give him out a picture of this product just to see, to be more convenient. What happens if the user came to us not for the first time? We keep all the user requests connected by his Telegram bot unique ID, and this is a user database. We use it to emulate the user's preference system. And like what happens differently if it's like the 4th, the 5th, and so on request is just we give more weight to those items which are closer to his history of search. That's it, like quite intuitive. And that's actually it. We can tune the amount of images and links which we output to the user, but after all this stuff, we just give back to our Telegram bot a material to construct the list of links to output to the user consequently, and the images from our database. In later versions, these images are automatically passed from the links to save time, to make all the request work faster. And that's it. The user gets what he's supposed to get, the recommendations, and where to get them. That's it.
And here is a short demo of how our service works.